Okay, let's look at the general linear regression problem. Now this is a maximum likelihood estimator. We will not do the full Bayesian approach, but I think it's important that you understand the idea of the likelihood. What is the likelihood function actually? And we're gonna maximize this likelihood, and because it's monotonous, we can also maximize or minimize actually the log likelihood. And again, I just draw here some sample points. Given x, and x is our feature vector, it could be a full feature matrix. So it is a matrix containing actually many features, and we can also use it for a multivariate linear regression. I just explain you what it is, but it mainly goes also in one dimension. We want to get the best maximum likelihood estimate for given data points. And it turns out, and this is also what Gauss has shown, it's also the least square solution. What does it mean? Least square means actually that we look for a straight line approximating actually all these data points, the yellow data points, such that the sum squared error here is minimized. And I just draw it using these squares, and then you also see what an outlier has for an effect. If this is an outlier, the weight of this outlier is this. This is an outlier. So you see, okay, it will be in a least square regression, will be dominant. Just as an idea. So the sum of squared errors is the area of all these squares. And Gauss said, okay, when he was measuring actually as a geodetics, actually kind of the principality of Braunschweig, I think, to minimize certain estimate of a geometric point in that line. And he said, okay, let's minimize this squared error. The sum of squared errors would be the sum of all these squares. Sum of squared errors, and now how can we calculate that? First of all, we have to make a model, and the model is explicitly linear in the parameters. So we say this straight line here is a model for the real data that I've measured. And this is a deterministic function. We call it now theta 0 plus theta 1 with unknown theta 0, theta 1 times x. And in the general multivariate case, this in general is a matrix. And our estimate here would always be on this straight line. This is a deterministic function. But the real values, we would model like this. The real values are actually an f plus an error. And the error comes from a Gaussian distribution. It's here assumed, means that actually the probability that I find a point out here gets less and less probable the further away it is from actually my model. And this is now the stochastic part of the model. Stochastic part. And when we say we make an estimate, we would say, and normally it's written like this, we make an estimate, it gets a hat. It's the estimate of our true value y, and this would be the true value y at the point e, xe. And our estimate is only here. This would be y hat. This is on the line. With estimated parameters theta and theta 1. So far they're unknown. But we can say, when we have y and y hat, then we can calculate the residuum. What is the residuum? The residuum is always the difference between the true value and the estimate of it. So The residuum is the difference between those two. This is called the residuum at point E. It's the difference. And we want to minimize those differences for all points. Okay, now we see, okay, this square here, this is just Ri squared. This is the square of our residual. So we can call this also here. Sum E1 times number of data points from the residuum squared. This is the same thing. Now we can calculate that out, because assuming that our estimation is on that line, and that line is given by f, we can calculate this difference. Okay, it's equal to the sum over E from 1 to n, from data point E, the value of data point E, minus y hat squared. Do you see that? I cannot put it higher. Sorry. Yes, and now we put in this here. This is our y hat. This is our estimate. It's an approximation of the real process, which has a stochastic part, which you don't know. So we sum up between those two. Now I go for the second thing here, and we put in here that formula. Okay. The sum of squared errors, and we will see it only depends on the thetas, and actually it's a theta vector, is y I minus f at the place xi squared. This is now the difference. And here we put in now our model. This is y hat. You have to stop me if it's too fast, or if something is not clear. Yeah?
Y in the hat.
Yes?
Do not have an index E also, or is the function?
Yeah, here I put in the full x, you know.
Okay.
Yeah? And of course, here we have index E because I put in xy. This is the full x, and this would be the full vector of.
The formula.
Ah, here.
Yeah.
Thank you. You're right. There must be a y there. And of course, here we put in the y and get the difference out of it. Now, for a linear function, this f can be easily written in matrix form. Assume, how would we write this in matrix form? So that we can just say f, we want to write it now in this form. F is x applied to theta. That's matrix product. How could we achieve that? Then we have linear functions. This is a true linear function. This is a affine function. It's not linear in x. Only because it has here this offset. So how do I make from an affine function a real linear function? I add a dimension. So we would say, okay, if I would define my x like this as a matrix from 1, 1, 1, 1 up to n here, so the nth entry is still a 1, and then I put x1, x2, x3, xn, and put this as a data matrix, like in a pandas data frame. Then I say, I have two features, feature 1 and feature 2. Feature 1 is a constant. Normally we would keep it out, but here it's important. It gives the bias, it gives the offset. And now you see, okay, I can multiply this by a theta. Theta 1 or theta 0, theta 1. This is the matrix product. So row times column gives, and here of course I also have to write this x times theta, x times theta. This is our, we will call it estimate of y. Is, okay, theta 0 times 1 plus theta 1 times x1. Theta 0 times 1 plus theta 1 times x2. And so on. So we can formulate this f here simply as a matrix matrix vector product with unknown parameters. And what is really helpful with this formulation, you know, if I make a polynomial regression, what would I put here as a third column? If I want to make a polynomial of second order, how would I then generate here a parabola? What do I have to add to my feature matrix X? This is called the feature matrix. Our data matrix, yeah?
You just need a new column and a new theta.
Right. And what would we add here as a third column? Can I make it here?
Yes. Just x1 equal.
Yeah. Perfect. Huh? x1 squared, we would just add a theta 2 here. So we are not restricted to linear problems. Yes, we are, but linear only in the parameters. I could also say, yeah, there's a model which has here square root of 1. We could also do, it's still linear in theta. And we only need the linearity in theta, not in x. We need linearity in theta to solve least square. But let's stick with the linear one first. Huh? Did you see how we can just add any dimension to make the model more complex? And then to make any polynomial fit. Huh? So we go back. Now we see, okay, how is depending on that. Huh? This is a matrix, this is a vector. Sometimes I write a vector, probably sometimes I forget about it. We go further. Now the important thing is I can write it like this. Is y minus x theta squared. And from this is now, it looks like formulation, but it helps because it's easier to calculate. Okay, now I continue on that side, okay? Now Gauss said, okay, we want to find the best fitting curve, means minimizing these squares. And in a later formulation, I'll show you that's the same to minimize or to maximize the log likelihood. It's the same, because this term we'll find also in our exponential Gaussian distribution when we calculate the likelihood. How likely is it to find the data outside? Huh? It turns out to be the same problem. Minimizing the least square is the same as maximizing the log likelihood for a Gaussian distribution of the data. And this we'll do at the second step. First we just say, okay, we say SSA from theta, the sum of squared errors from theta should be minimum. That's the best curve. Now you see, okay, an outlier has such a square. It is really important to remove those outliers first. And this is what you call then a robust linear regression. I just say, let's take the quantiles only, the 90 quantiles or so, to fit the curve and get the outliers out. Minimizing the squares means actually something like that. In analysis, we have a multi-dimensional function. We would say, okay, we have to minimize, we have to calculate the gradient. So we would calculate d from SSA, d theta 1 equals 0, and d SSA theta 1 equals 0. We look for the maximum or the minimum. Means they have a horizontal tangential plane on all these parameters. Huh? So a function is maximum where the tangent, where the slope is 0. Now in every dimension. And often probably you see this also in books like that you say the gradient with respect to theta of our function that we want to minimize is 0. This gives us the critical points. This is the candidate list of points where we have best matching parameters. There could also be phase. There could also be that one. Huh? But now looking at this function is, we have a quadratic function. It's a quadratic function which is monotonous on both sides. So it can only have one minimum. So this minimum is unique. And we don't have to look at the second derivatives to say, could it be a saddle point? No. With such a function, never. This function never has a saddle point. It is always monotonous like that. So in theta 1 and theta 2, this is a quadratic function. So it has only one minimum, and we're looking for that one. Now, since these are vectors, and this is also a vector, we have to calculate with more dimensional analysis. Yeah?
They are also the vectors from series.
Here?
Vectors, that's it too.
Sometimes it's written, I could also make it bold, right? Okay, so this can also be formulated in another way. This can be formulated in this way. The squared distance it's the distance between these two vectors in Euclidean norm. So how far? This is now all the data points. y1 to yn is a vector of y's. This is a vector of y dot vector. So the difference between our estimate and the real y, we want to minimize that. Huh? They should match as close as possible. And then you see, okay, we could just write it in the norm, which is the Euclidean norm, which says this squared plus this squared plus this squared and so on. Huh? This makes already the sum here, from E equals 1 to n. When I write here the vectors, then I don't need the sum. Huh? So either the sum, so yeah. And then I have the e's. Okay, to calculate that is a little bit of work, and the idea to do that is we write out this product. Actually, the norm of a vector is always the scalar product. A times A, scalar multiplied, is the norm of the vector. A, scalar product A, is equal A squared. This we know actually from. So it's a projection of A to itself, it's the length squared, the length of the vector squared. And in matrix form we can also write it like this. It's A transposed matrix product times A. AT, T, ATA. So row vector, column vector. It's a scalar product if we multiply it. So I can write this here as y minus x theta t times y minus x theta itself. SSE is now this norm. And according to this, I can write it like this. It's y vector minus x theta vector. Now I take the t times the same vector, but not transposed. And here it's a matrix product. So far it's okay? And now it turns out to solve this now, we have to multiply this out. So we get a quadratic term, y t theta, well, we get all the mixed terms and we get this term. And then, using just analysis in high dimensions, actually, we will get out the optimum solution for these theta's. This is now some work. Shall we do that? Multiply it out, or shall we leave it? It's also in the solutions. I can multiply that out and then use just the rules for high dimensional derivatives to show actually that the optimal solution is exactly this least square solution, the pseudo inverse, Moore-Penrose. The next step would also be this, to multiply that, use kind of a symmetry for scalars, and then make the derivative with respect to theta vector here. And then you get out the normal equations for the optimum theta. And this optimum theta now, this is what I want to show, is also the maximum likelihood estimate. So it turns out that Gauss solution is the maximum likelihood estimate. So this is just some work to do. Probably you can look it up. But for me, the understanding is we do also a minimization problem. It's an optimization problem. We can solve it directly here. For any linear problem, linear means linear in the parameters, not linear in x. And here we can generate any function we want. We can make radial basis functions out of this x. And just say, oh, it's focused around this, and we put those radial basis functions as many feature vectors into it. Okay? The solution will pick up those radial basis functions which are matching best. It's like a development into these real basis functions. Now, I think you believe me that deriving this by theta, we will get the normal equation which solves actually this problem uniquely. But better, I think more important to show you is now that this solution is the same solution as our maximum likelihood solution. And this gives actually the notion of what is maximum likelihood. Okay? And the solution for this you can read in the solution of the second exercise of series 9b. Yeah, I've written it out. It's nice. For me, it was important to see how this works. Then I understand those things. I have to follow it once, but you don't have to be able to reproduce it. It's good that you see, okay, it's done like this. And then you've done it once, and I think this gives a deeper understanding of how things work. Now, the notion actually, and this is important, the notion from a probabilistic view is that you would say, yeah, we have our deterministic model, y. Now we don't see anything, huh? To wait, I think. Our probabilistic view of the things would be, we have our model, f from x. X is a data matrix, is x times theta. We stick with that. Now we have to define somehow the likelihood function with that. And this we would say, this is our estimate from y. And this is of course also a vector now. This is the estimate of y, and we have given data points. These are the y's. Means these are the vector ye until n. And the probabilistic view would be, let's define the likelihood function. And now, I think, now comes the big conceptual step. A statistician would not say y equals f plus epsilon. We have seen the true y equals f from x plus epsilon. And this is a Gaussian noise. The true statistician would say the true y is drawn from a normal distribution centered around f from x. This is now the mean value with a given variance sigma square. So he would say the same thing, it's the same thing. He would just say it's additive Gaussian noise. We have the real value and make some additive Gaussian noise. But a statistician says, okay, our y is given by a normal distribution around our estimate with a variance sigma, and this is the new average value, the middle there, so the new value. And from that point of view, we can see now not only the straight line, but all Gaussian distributions around this straight line. And now we can calculate the likelihood function, which is the difference between our estimate. How likely is it that I obtain a y given actually this distribution? And the likelihood is actually the probability that I find a given data point given a model. So it's the probability of y. And for one single data point, the likelihood is one single data point, since they all come from actually a Gaussian distribution around. That's now centered like this here. So it's the distance from here to here in a Gaussian distribution. We would say the probability of finding y given our model and x and our model f or theta is, for one single one, we have a normalization constant, which is pi 2 pi sigma 0 squared over, or to the power of 1/2. This is for one single point times the exponential function minus 1 over 2 sigma 0 squared from epsilon y minus theta xy. Huh? So xy theta. And now we can interpret this like this. The further away this y is from our estimate, the less probable it will be that we find it. It goes down here, this distribution. But this is the likelihood for one data point. So the likelihood for finding all xy and yi's at this position is just the product of all these. The total likelihood is one data point. For one data point, I have just a single one. Now the probability of finding here a point here and here is the product of the probabilities, because it's an AND connection. I have to find this one there, the other one there, and the other one there. So all in all would be the full probability to find all my data given my x and the given parameter vector theta is just the product over all these distributions. Because it is an AND. It's this one has to be there, the other one there, and there, and there. So what's the total probability? It will be very small probably, yeah? But we can calculate it. I times 1 over n, and this comes in, and this one comes in times n half. But I just write it now in this form. YE given XE und theta. Now we have a product of exponentials, and the product of exponentials, you see it? E times A times E times B is E times E to the power of E plus B, plus B. So out of this product of probabilities, we get a sum over all E. And now we end up at the same point where Gauss started, right? Sum all squares. And it turns out to be the same problem. So we make the next step here. I just put it in here. Shall I put it on a new table? Or here. So we get here an n half. 1 to the pi 2 pi sigma 0 squared to the power on n half times exponential. Now from a sum over all E, up to n over these distances. Minus 1, this I could leave out of this, 2 sigma 0 squared times yi minus theta xi squared. Curly brackets. And now we see this is the sum of squared errors. And now to maximize the probability, we have to maximize the probability that we find the data. It's the maximum likelihood approach. We have to maximize that exponential function. But we can also take a monotonous function like the logarithm to maximize that one. So for example, if I know square root is monotonous, I can also just maximize the argument. It's the other way around. So what is normally done to calculate it easier, we take the logarithm. Now you see what happens. The logarithm of the exponential function turns out to be just the sum of squared errors. So the maximization of the log likelihood is identical to minimizing, because there's a minus here, minimizing the squared error sum. So maximizing this one, because of this minus one, is equal, because we can take the logarithm, the exponential will fall away, is identical to summing all squared errors and minimizing them. And that's I think, for me this opened up what does likelihood mean. Likelihood means how probable is a data point given my model. And Bayes turns it away around and says, how probable is this model given those data points? So we have to inverse the whole thing, and this we can do by using Bayes' theorem. So if you have understood that, I think this is really a thing, a fundament you can base on. There's not much more to tell about it. Because now you've heard all these expressions once. If you think about it a little bit, actually, it all comes together, I hope. Yeah. Now, you see, this is still a point estimate. Bayes goes a little bit further and says, I'm not happy with just this point estimate. I want to have the significance afterwards. Okay. Was this understandable? Good. Okay. And who knows MATLAB? Good. How do you calculate the least square thing? Using the backslash operator. Right. Backslash operator here in MATLAB